Oh, we're okay. 2 minutes early, I think. As you wish. You're in charge. Okay. Thanks for the invitation and the opportunity to give this talk. Perhaps I should start by explaining what the first adjective in the title means. It's got nothing to do with constructive field theory a la Gleeman Jeffy. What it means is, and that's a sort of takeaway, a broad takeaway from the talk, is that I'm going to present some mathematical construction of refined topological strings, if you know what this means. Is this legible from the back? Okay. In terms of some virtual counts of parametrized curves inside a Calabi-Yau tree. Or if you wish, through some definition of refined Gromov-Witten invariance of Calabi-Yau trees with a C-star action. And so the slogan version of this sentence is that refined invariance, curve counting invariance of Calabi-Yau trees are equivariant invariants of certain Calabi-Yau 5s that are constructed out of my threefold. And so, yeah, so this talk is just epsilon shy from being the first in a series of 4 this week that have the word equivariant in the title. And although the mathematics is very different, the core idea has a substantial intellectual debt with work of Nekrasov and Okounkov from about 10 years ago, and probably even earlier, work of Nekrasov on the index of M theory. If you know about this story. So this talk will be, so the story will be very much the sigma model Gromov-Witten take on their PT theoretic, shift theoretic, mathematical construction of the theory on the D6. No. I mean, refined MNOP is something that I mean, there's not going to be an MNOP statement until the very end, and it's going to be conjectural. Now, it's a different thing, and I will tell you. Okay, so I will tell you in the third part of the talk why this makes sense. By I present 3 theorems that will show you that this is probably the same refinement that you would expect from a shift theoretic or gauge theoretic perspective. Okay, so yeah, before that, if you don't know what I've just said during the last 3 minutes, so you have no idea what topological strings are, I'm just going to give you a quick overview of the problem. If you do, you're going to be just ruthlessly neglected for the first 20 minutes. I will tell you when to wake up. So it's going to be pedagogical at the beginning, although the students from last week have all but vanished this week. Then I will describe the setup and the precise form of the conjecture. And I will present some results why you should believe that this conjecture is on the right track. So this is work with Jan Schuler, who, as of yesterday afternoon, is no longer my PhD student and is a postdoc in Cambridge. Any questions before I start? It's got everything in due course. Yeah. Yeah, it'll come. You can probably doze off for the first 15 to 20 minutes of the talk, Stefano. So let me start with X Calabi-03. Say smooth quasi-projective over the complex numbers. Now, given the datum of X, I can construct a field theory out of it by considering a theory with minimal supersymmetry in 4 dimensions, n equals 1. That has no gauge degrees of freedom, it has no superpotential, and the entire dynamics is specified by the killer potential of my Calabi-Yau. And starting from that, I can reduce down to 2 dimensions to get some 2-dimensional sigma model on my Calabi-Yau with the same amount of supersymmetry, which is n equals 2, 2 in 2D, with X as a target. So this theory has 2 twists. So there are 2 ways to combine the global symmetries of this theory with the Lorentz transformations in 2 dimensions. And I'm going to label them by a letter, A or B. A model, B model. In terms of which one can construct a spin 0 supercharge, QAB. So this is a spin 0 and odd. Such that in the Q cohomology, in the respectives, for the respective twists, two dramatic things happen. The first is the theory is topological on the worksheet. And the second is that the theory is semi-classical, meaning that physics theorem or mathematics definition, the path integral localizes on shell trajectories only. So to solutions of the Euler-Lagrange equations. So in the case of the A model, which is the thing that I will consider for 20% of my talk, this Q cohomology is isomorphic as a vector space to the Drang cohomology of the target. And for scalars, the Euler-Lagrange equations are the Cauchy-Riemann equations for my maps. Meaning that instantons in this theory are holomorphic maps to X. And so coupling to worksheet gravity, one can define a topological string partition function whose logarithm I'm going to denote by W of variable X, epsilon, and Q, which is a sum over worksheets of genus G. Greater than or equal to 0. And epsilon is a formal genus counting parameter. And then I have some expression GWG of X and Q, where this GWG X and Q is a sum over instantons. So it's a sum over 2 homology classes that represent effective curves in X. And I'm going to stick some formal parameter, chemical potential, to account for those. And then I got some instanton number, GW, G beta of X. So there's some formal power series. It's actually convergent with some finite radius for Calabi-Yau in this variable Q. Yeah. Yeah. For Calabi-Yau 3, yes. No. There's a paper of Coates and Brini about that. Yeah. I mean, there's a whole statement about the homogeneous full descent and given potential. And then you can take some conformal limit to recover the Calabi-Yau slope. So fixing the genus, I'm talking about the degree expansion. The genus, the genus for fixed degree is divergent. Yeah, so probably that's what you had in mind. Yeah, okay. Okay, so how do you formalize this mathematically? You have a moduli space of instantons labeled by these discrete topological data, the genus and the degree. So there is some moduli space of maps phi from some projective curve from projective curve C to X, such that, well, C is a curve, has a projective curve. Of arithmetic genus G. And degree beta. And if I take C to be smooth, this will be some open moduli space. Because I want to integrate on it, and I want to integrate cohomology classes on it, I would want to compactify it. So this modulo automorphisms of the domain. And the compactification that I take is the sort of minimal one. So I'm giving up on the smoothness on C by allowing double points on the domain curve. So C is nodal. And moreover, I want this space to be this space will have arbitrarily bad singularities, but the orbital singularities I'm going to insist that will be of finite order. So this will be in technical terms a Deligne-Mumford stack. And the stability condition in question stipulates that if I have a contracted component of C by the map, this need to have a finite order automorphism group. So at least big enough genus or sufficiently big number of nodes. So these instanton numbers in the roughest possible sense, this moduli space hosts a special homology class, which is dual to what you would want your volume form of the moduli space to be. And so it has a perfect obstruction theory and the virtual fundamental class in dimension 0. And I'm going to define these numbers to be the degree of the virtual fundamental class. So this has appeared in the talk of Taro, I believe, last week. That's not how I write it. So this is a class in the zero-dimensional child group of the moduli space. So, sorry? There's a whole math overflow thread about why you should take the Kontsievich/Deligne-Mumford compactification rather than a different one where you're allowing cuspidal singularities. So I don't think I can see this from this perspective, just from from the fact that you've written down a Lagrangian. So you need some extra input, to my knowledge. So these are called sorry, I haven't given them a name. These are the Gromov-Witten invariants of X. Now, Gromov-Witten invariants are great for what they are. So what they do is to give a mathematical definition of what we mean by the topological A model on indeed any almost scalar manifold, in particular on Calabi-Yau 3s. And they do so, one of the properties of the virtual fundamental class is that they provide this answer in a deformation invariance way, which is consistent with the physics perspective by which complex structure deformations in the A model are Q-exact. And mathematically, they provide a set of symplectic invariants that answer some enumerative problems. So you could forget about X being a Calabi-Yau. You could take, say, Pn, and you can ask yourself about the count of a certain number of curves of a certain degree in genus that pass through some collection of cycles when impose some incidence conditions. But I guess for this crowd, Gromov-Witten invariants are even nicer for what they do. And they do two things. Well, they do a lot of things on two strands. So in physics, there's a reinterpretation of this stable maps counts in terms of what they do, what they compute for the effective type 2 theory compactified on this Calabi-Yau. So if you take the full partition function, or free energy, x epsilon q, so its genus expansion, order by order, computes some effective term, some f term, in a type 2a compactification on X. So involving the interaction of soft graviphoton modes with the vectors in your theory. So this would be Kähler moduli for the A model. And because of this viewpoint, there is an alternative way of computing the same F terms, which is by integrating out contributions of wrapped M2 branes, giving massive BPS particles, computing these same F terms. And that's an alternative way to compute the same thing, which has a very different shape due to Gopal Kumar and Vafa and at the end of the 90s. So I'm going to write this. Has this been too fast, too slow? Any questions before I write? Good. I guess I'm going to write like this. So I have a different generating series that coincides with the previous one. And the statement is that the disconnected generating series of Gromov-Witten invariants of a Calabi-Yau 3 is the platistic exponential of some BPS partition function, general series. So I need to write this slowly, I guess. I have a bunch of sums. I have a sum k from 1 to infinity. And then again, I have a sum over degrees. And I have this degree counting parameter scaled by k, divided by, okay, I got some combinatorial factor that I'm going to describe momentarily. Just bear with me for a second. And then I got some unknown function, q to the k, where, okay, I need to define what I mean by this symbol, and I need to define what I mean by this omega b. So, and I also need to specify what q is. So q is just e to the epsilon. And this expression is just the symmetrized q number, unnormalized. That's a physics notation. So for an integer, positive integer n sub q is equal to q to the n half minus q to the minus n half. And then I need to define what omega is. So omega sub b of q is some Laurent polynomial, integral Laurent polynomial, in this variable q, plus minus 1. And it's defined, just bear with me, it's the end of this ordeal is drawing nearer. It's defined in terms of a different set of numbers than my GWs that I had before. So I got numbers depending on, I got two summation integers, which are spins, JL, JR. And I got integers, conjecturally positive integers, JL, JR. And then I have some sign factor, 2 to the JL plus 2 to the JR. And I got a sum. I'm nearly finished. I guess I'm gonna go down here. I have a sum, dl from minus JL to JL. And I got some q to the twice dl. And I got a sum from dr minus jr to jr of 1, which I'm going to write like this, 1 to the twice dr. So I've defined everything. I've defined what omega b is, so long as I define what this number is. So this number is the Gopa-Kumar-Waffen, it's the refined Gopa-Kumar-Waffen invariant, JLJR, is the count of M2 branes wrapping holomorphic cycles in homology class beta. So homology class beta. So they have mass or charge quantum number specified by beta. And they have Lorentz quantum numbers in 5 dimensions specified by this pair of spins, JL, JR. So spin 4 is SU2 times SU2. So in principle, so one can reconstruct the Gromov-Witten invariance given prior knowledge of these numbers. The reason why I am sticking this value 1 in here is that the left-hand side, or the top-hand side, the Gromov-Witten partition function is deformation invariant, and I would only get an index for the right-hand side, so for just the lower row, if I take a particular linear combination of this BPS counts that has this 1 over here. If I didn't, then this quantity would depend on the complex structure of my Calabi-Yau. How am I doing with time? It's not even that terrible. So that would be my next board. So I was saying that Gromov-Witten do something for you. One is they can at least recover part of this underlying integral structure associated to Kerr counts on the Calabi-Yau from this BPS counts. And as we've heard already last week, one of the things that they do is that they sit at the center of some web of correspondences, both in physics and in mathematics. One is for certain Calabi-Yaus, one can engineer some rigid n equals 2 theory by considering this compactification. And so Gromov-Witten counts correspond to Istanton counts on the 4-dimensional theory. And by dualizing to a theory of a D6 wrapping the Calabi-Yau, this BPS count can be translated into a count of BPS solitons in a 6-dimensional gauge theory, abelian gauge theory on the Calabi-Yau, which in mathematics translates to a relation to different sets of Kerr-Counting invariants. For example, by ideal sheaves or stable pairs. So this is the MNOP correspondence that Vivek was evoking before. And again, for some Calabi-Yaus, there's another gauge string duality, but with a 3-dimensional supersymmetric theory, which is Chern-Simons theory. And in turn, this relates Gromov-Witten invariance of some x's to quantum invariance of 3 manifolds in various guises. And there's more. I mean, I don't know. There's like statistical mechanical models, like, for example, crystals or pyramids, whose partition function returns one of these partition functions, the DT partition function. And in turn, again, hinging on this relation to Chern-Simons theory, there's a combinatorial way to compute Gromov-Witten invariance for toric Calabi-Yaus through a topological vertex. And there's a relation to 2D CFTs mediated by the relation to gauge theory by AGT. And in turn to matrix models. And a lot more. So this is the kind of slide that you show to funders when you want their money. All I want is your attention for something that's going to be relevant in a second. And it's related to something I said before about this quantity. If I introduce, for example, an extra chemical potential to keep track of the right spins for my BPS state counts, then there's no way I could match that to something that has a Gromov-Witten type flavor, because it wouldn't be deformation invariant. But what if, and this goes back to Stefano's question at the beginning, what if you restrict to a case when your Calabi-Yau is rigid? For example, when you have an holomorphic isometry acting on your Calabi-Yau, say X is toric Calabi-Yau 3, X is the result conifold. So in that case, you can consider something that's more refined than this this generating function. So let me just erase this Gromov-Witten thing. I can consider the, okay, maybe I can use some color chalk. I guess I'll resort to this. I can stick an extra variable. Yep. Hang in there. I will want them to scale. Yes, that's going to be key. So I will have some refined partition function on the Gopa-Kumar-Vafa side, where I have extra variables, epsilon1 and epsilon2. So I have like qi is e to the epsilon I. So I have two variables, q1 and q2. I guess this is q1, this is q2. And then I have some refined Laurent polynomials, omega beta, q1, q2. So this will be polynomials in two variables, q1 and q2. Sorry, q1 to the half and q2 to the half. And they are obtained by sticking, what do I have here? I guess I have a q1 over q2, and the q1 times q2 without the power of 2 here. So by expanding in q1 and q2, I can recover the full BPS content of my theory. And then the reason why I wasted a minute and a half of my time listing these things is that not only does this refinement make sense from the point of view of BPS state counts, so there is such a thing as refined Gopakumar-Vafa invariance, for each and every one of these points, there is a canonical refinement, a canonical one-parameter deformation of the relevant generating series that precisely returns the one-parameter deformation that I took on the Gopakumar-Vafa side of things. So for instanton counts, this would be the omega deformation. For shift theoretic curve counts, this would be some motivic refinement or a refinement happening in equivariant K theory. For quantum invariance of three manifolds, I would replace the SNT matrices of the WZW model by some kind of McDonald refinement. And likewise, this would correspond to the same type of refinement for the topological vertex. There is a notion of refined topological vertex. And for the 2D CFTs, this would be some deformation away, say in Liouville theory, from C equal 1 by turning some background charge. On the matrix model side, this would correspond to some modification of the two-body interaction, something like the beta deformation in some cases. So everything makes sense for, yeah? I think I'm not going to say anything about the B model until the end, but maybe I'll make a comment on what you just said. So the outcome of the proposal that I'm going to present in a second is something along these lines. So this is a sensible thing to do in all of these variety of settings that I've mentioned. And the sort of natural question is, if you circle back to our original setup, which was some topological string perspective, you got some sigma model, topological sigma model coupled to topological gravity, what would that one parameter deformation look like? Okay, so what is, maybe I can phrase this question in two ways. Let me just write down the question and ask you if it makes sense. Is this better? Okay, it's good. So the question, so the key question today is, what is this one parameter deformation? Is that seen from the worksheet theory? So what is this refinement for topological strings? Or mathematically, what are the refined Gromov-Witten invariants that under some natural, under the same sort of change of variables happening in the MNOP correspondence respond to refined ET invariants or PT invariants? So there has been some work on the physics side of the story. Nakayama Oguri and Antoniadis, Honegger, and writers. I won't comment too much upon that because the viewpoint presented today is a bit different. And there's been essentially no work on the mathematical side of things for this question. Yeah. It doesn't respond to this. Yeah. There's no left-hand side. There is a conjectural left-hand side, which is this M2 brane moduli space. So the DT version, there's a PT version. Everything makes sense on the DT side of things. What I'm concerned about is the GW. Okay. Mm-hmm. There isn't. There is the left-hand side, K-theoretic Gromov-Witten invariance of your Calabi house doesn't work. Everything clear? Apologize for the slow 35 minutes. Okay, so yeah. Yes. Give me a second. Give me a second. It's coming now. Yeah, it's going to be defined only. You need X structure, then I'm going to describe it. And sorry, this is again Stefano's question, I suppose. Or what's going to be Stefano's question because before I cut him out. Okay, the setup is as follows. Yes, thanks for bearing with me. And I'm going to be slightly more specific now. So X is a smooth quasi-projective threefold. And it's going to be a Calabi-Yau in this setting. So this Nekrasov-Kunkov story is actually more general than that. So in my case, X is O of X. And yes, the C star action, the extra structure, here it is. I'm going to require that there's a torus, a one-dimensional torus. I'm going to call it T prime that acts on X. And such that, going back to Vivek's question, the holomorphic 3-0 form on X is scaled non-trivially. So the character, I'm going to call it Q plus. So this is by definition the weight of the T prime action on omega X is non-trivial. And there's bad use of the blackboard. I'll need to squeeze some stuff in here. So I'm going to consider a Calabi-Yau fivefold, and throughout this talk, this will be simply the product of X times the affine plane. And I'm going to consider a lift of the T prime action on X to a T action, which is an action of a 2 torus on Z, such that the action on the anticanonical is trivial. This is, I have a C star action on, say, C2, and I lift it to a C star action on the full Calabi-Yau in such a way that the resulting Calabi-Yau is equivalently trivial. Okay, so maybe more. So I have, say, I'm going to have weights, geometric weights, omega 1, well, Q1, Q2, on the affine coordinates of C2. So what I'm saying is, I'll make an example in a second. Yeah, sure. Sure. I mean, so a weight for me here is just a representation of the torus. So I mean, it's an element in the T-equivariant K theory of the point. So there's nothing about positivity that's going to happen in a second. What I'm going to considering in a second is some formal expansion in variables epsilon 1, epsilon 2 related to Q's exponential that I wrote before. And I'm not going to say anything about the positivity of the epsilons. So as a result of what I said, I have some fixed locus of T action on the threefold, which coincides with a T fixed locus of the T action on Z. And my request that the lift action to the fivefold is trivial on the anticanonical is a statement that what I call Q plus is equal to 1 over Q1, Q2. Okay, so I got some non-trivial action on the Calabi-Yau on C2, and I got some non-trivial action on the Calabi-Yau 3 form on X. That's what I'm saying. This is the same condition that appeared in Taro's talk last week. And the epsilon i's are going to be the first Chern classes of my QIs. Okay, so maybe just the example to keep in mind is you can take the result conifold. How am I doing with time? Okay. And so Z is the result conifold times C. And I will take for T the action that covers the trivial action on the base P1. And that scales the fibers with weights 1, 0, 0, 1, minus 1, 0, 0, minus 1. So respectively for the O minus 1 affine fibers and the O fibers. Now, last thing, I write the definition. I'm going to make an assumption. And the technical assumption that I'm making is that whenever my curve class is non-trivial, the moduli space of stable maps to the threefold X is proper. Otherwise, I would need to restrict to curve classes that do satisfy this, this condition. So, yeah. Yes, yes. Yeah. Exactly. Yeah, yeah. So the kind of things that I have in mind, in those cases, or in those cases, you will restrict when you write it, stuff that does satisfy the assumption. But yeah, the kind of to have in mind is some of the basic examples that we know and love. One is the conifold, and the other is the one that that Vivek was mentioning. So total space of the canonical on a Delpezzo surface, not necessarily toric. The C-star action just coming from the scaling of the fiber. Okay, definition. I guess I don't need this piece of propaganda on this board. So the definition is that I'm going to define the Gromov-Witten generating series, free energies of X, of such an X, epsilon 1, epsilon 2, and Q, to be equal to some genus expansion. And I'm not going to put any formal variable to keep track of that. Then I have some degree expansion. And I'm going to have a variable Q to the beta to keep track of that. And then I have the T-equivariant Gromov-Witten invariance of Z in genus G and beta. So this thing is an element of the field of fraction of the equivariant cohomology of the point. And because of the virtual class of the threefold having virtual dimension 0, it's actually quite constrained. And because of the fivefold taking this form, it's a polynomial up to a factor 1 over epsilon 1, epsilon 2 in epsilon 1, epsilon 2, and epsilon 1 plus epsilon 2, homogeneous of degree 2g. So that's where the epsilon 1, epsilon 2 dependence comes about. So because of this, I can expand this refined generating functions in variables g and k. There's a traditional way this is done in the physics literature, k and g, of some numbers now, that I'm going to call the refined Gromov-Witten invariance with indices k and g of x as functions. Sorry, they're not numbers. They are convergent power series in Q, around Q equals 0. Yeah. Exactly. As dumb as that. Okay. Okay, conjecture. So this is the guy we were after. So conjecture, this is the thing. Okay. Just going to suppress everything. Okay. And why should one believe it? And that's yeah. So the conjecture means that if you take the asymptotic expansion of the right-hand side at epsilon 1, epsilon 2 equal to 0. Okay. Oh, the right-hand side is, so one way to define the right-hand side is, for example, to appealing to the DT refinement, so to reconstruct the BPS invariance from that. For toric Calabi 3, that's the result of the refined topological vertex calculation. Yalla, yalla, yalla. Yeah. Yeah, so I guess at every point when I say that I'm giving you evidence for a conjecture, I need to specify what I mean mathematically by the right-hand side. Yeah, thanks to that. Okay. Ready? Tests. So there are 3 categories of tests that we can think about. The first is a sanity check. That is, if I take a Calabi-Yau action on C2, lift into a Calabi-Yau action on the 5-fold, does this give me the unrefined limit? So if I said epsilon 1 equals minus epsilon 2, does the equivariant theory on the 5-fold collapse to the ordinary higher genus theory on the 3-fold? And then, well, there are 2 sets of things that we can think to use to prove this. Well, first to even define this and then prove it. One is to match with the results of refined PT, DT, or topological vertex. And the other one is there is a calculational definition of the right-hand side in the B model using the refined holomorphic anomaly. And can we see that to appear from the Gromov-Witten theory of the 5-fold? So the refined holomorphic anomaly equations plus boundary conditions. Okay. What am I going to raise? Maybe I'm going to keep this example. Minutes. So with no hypothesis on X other than allowing for the existence of this torus action, we have the following. So that the Gromov-Witten, the unrefined, sorry, the refined Gromov-Witten generating series with epsilon 1 equal to minus epsilon 2 is equal to the unrefined limit. And the proof is one line. I'll just write it quickly. If you look at how the T equivariant virtual fundamental class of the 5-fold is the one of the 3-fold, Then the relation between the two is given by the cap with two copies of the churn of the Hodge bundle on the moduli space of stable maps to X. So so just to write down what I said, lambda of epsilon is the churn polynomial up to an overall factor of 1 over epsilon of the Hodge bundle. No, fine. You take the refined one, you restrict to the unrefined limit. So this is refined. I'm not setting epsilon 1 equal to minus epsilon 2. Yeah, so there's something drastic that happens when epsilon 1 is equal to minus epsilon 2. So lambda k here is a kth churn class of the Hodge bundle on the moduli space of stable maps, the same way as the Hodge bundle on the live stable curves. And to get to the next question, if you set epsilon 1 equal to minus epsilon 2, there's a relation due to Mumford, pulled back from the moduli space of stable curves, that tells you that this is just pure weight, epsilon to the 2g minus 2. Okay. So this is just a sanity check. I am deforming the correct thing when I reduce to the self-dual slice of the omega background. And okay, but it can be any deformation, any wrong, possibly wrong deformation that doesn't give me the BPS refinement. So for some slightly more cogent test, I'm going to present two results. Of course, there are calculations that one can do in localization in small genus and degree and see that numbers match on the left and right hand side. But that's just a handful of numbers, so I'm not going to present those. So the first theorem is take x and t, as in the example. Then the conjecture holds. So this is true in the full refined setting for the result conifold. And okay, what is the right-hand side in this case? Well, we have a calculation. I think this goes back to work of Katz and at the end of the early 2000s. So we have a calculation of this BPS invariance for the result conifold that are all vanishing, except for one case. So this is equal to 1 when JL, the spins are 0, and beta is the 0 section. And otherwise, they vanish. So this means that that complicated expression that I had before with the sum over spins and degrees and all that collapses to just a sum over some multi-covering factor. So this implies that Gopa-Kumar-Vafa ref is equal to sum k from 1 to infinity, 1 over k, q1 number of k, q2 number of k, times q to the k. And so the name of the game is reproduce this expression from the Gromov-Witten theory of Z in that example. And I don't have time for the proof, I'm afraid. So for something more complicated, so if you're a practitioner of calculations in this business, you know that things get nasty when you have compact force cycles in your Calabi-Yau. So the sort of next step in complexity is to consider a local surface. So this is, I'm taking S at El Pezzo. and I take X to be the total space of the canonical of my del pezzo, then the statement is that I don't have a statement for the full refined generating series, but if you multiply by epsilon 2, and you take the limit as epsilon 2 goes to 0, by what I just erased on the previous slide, this is something that is well defined. And I claim that this is equal to the NS limit of the corresponding BPS count. And so the proof for both, okay, I'll just write one word. Sorry about that. I'm happy to give more details if you want later. So the proof is the use of the degeneration formula in log Gromov-Witten theory. So the special situation for these fivefolds is that there's a crazy expression that you can give to the left-hand side in terms of a sum over some bipartite graphs. But with all the conditions that I put, including crucially the NS limit for the second theorem, these sum either are completely summable and factorized to give the result for the conifold, and in the S limit for local del pezzos, they're reduced to a single term that you can identify with the corresponding Gopa-Kumar-Vafa count. Yeah. Yeah. So for the second one, what you can prove is that the left-hand side gives you up to combinatorial factor, the relative theory of S relative to an anticanonical divisor. So S times C times an anticanonical divisor times C. And because of the Schiff-Kurz correspondence, that gives you the generating, well, it's related through the usual platistic exponential to a generating series of intersection Betti numbers on some moduli space of pure sheaves. That's how the theorem works, yeah. Okay, last thing. Can I get 5 minutes? I think I have 3. Is that okay? Sure? Everybody okay? No objections? Sarah, you good? Okay, cool. Okay, so let me restrict now to S being P2. So this is for the sake of computation. There is no conceptual reason why I'm doing this in particular. So this has some mirror. Okay, when I said that the last 5% would be about the B model, that's when it comes into play. So it has some mirror family, which is what? So it's a family of elliptic curves. So this is in P2 times, so the base of the family is the weighted projective line P13. So the fibers of the family satisfy this equation, the cubic equation, in homogeneous variables. So the way this looks is you got some family over a line, an orbifold line, and the family has 2 singular fibers. It has a singular fiber above y equals -1 over 27. That's a conifold point. Coming in a second. So the general fiber will be some smooth elliptic curve. And I got 2 other singular points. There's a large radius point, so I call this the CP, is the conifold point. Then there's 0, the large radius point. And then I got an orbifold point at y equals infinity. So the conifold point will be a unipotent monodromy point. The large radius point will be a maximal unipotent monodromy point, and I will have finite monodromy arising from the fact that I got some isotropy at infinity around the orbital point. So I have periods for this family. I can fix A and B cycles in terms of their behavior around large radius. So I will have one diverging square logarithmically and one logarithmically. I'm going to call them respectively the B and the A cycle. And they're the period of some differential, which, well, in an affine patch where x0 is 1, is, I think we've seen this at some point, I guess. It was probably in Janstalk last week. This is x1 d log x2. And, okay, I guess I'll change notation slightly. I shouldn't have used x here. So there are two functions of y. There are actually quasi-modular forms. One is the inverse of the discriminant. And the other, in terms of this period, is something that I call P. The propagator is the y logarithmic derivative of the log of the y logarithmic derivative of the log of pi a. And so why the hell am I saying this? And that's what I want to explain now. Sorry? Yeah. So you have two affine patches on the base, but the way you glue them is like you take y going to, say, you call x. The other affine coordinate is y is 1 over x cubed. And so why this? It's because I want to get to the B model. And as I said, there is no first principles, or there may be, okay, but at least the first definition of refined generating in the B model is a recursive one, a calculational one, if you wish. So this is due to Krepel and Walcher, and specifically Huang and Clem, in the setup I'm considering. And the statement is that for local P2, functions are determined recursively from 3 basic cases. So these are 0, 0, 1, 0, and 0, 1. Plus 4 conditions. So the first property is the fact that these quantities are polynomials in these 2 generators that I wrote before. Actually, another statement is that these are special quasi-modular forms of the modular group gamma 1, 3. Just bear with me 2 minutes and the statement will arrive. So this is, these are Laurent polynomials with rational coefficients in what I call delta. And there are genuine polynomials in the propagator P, where the degree of P, the degree in P is less than 3g minus 3 plus 3k. The second property is a 1-parameter deformation of the BCOV equations. So it's the refined holomorphic anomaly, which I won't have time to write down. So if you don't know what this is, for our purposes to is there's a set of equations on these polynomials that fix entirely the dependence in P of this quantity up to the constant term. So there's a constant term in P, which is the so-called holomorphic ambiguity in this game. And in order to fix the holomorphic ambiguity, which used to be some people's favorite sport about 15 years ago, what have I got? There's some set of boundary conditions. there are two boundary conditions. One is the third property, which is the so-called orbifold regularity. And actually, what I'm going to prove is something stronger, which is the fact that the refined version of the Krappan transformation correspondence holds for Kp2 times C2, resolving the mu3 singularity in 3 dimensions with weights 1, 1, 1 times C2. And then final, there's some asymptotic condition at the conical point for this generating series, or rather some modularly transformed cousins of them, that says that the conical free energies, refined free energies, should satisfy some asymptotic condition given by the logarithm of the double gamma function with argument epsilon 1 and epsilon 2. So this is the free energy of the d equals 1 ordinary bosonic string at radius, so this is like the c equals 1 string at radius r equals minus epsilon 1 over epsilon 2. Okay, thanks for enduring all this. Theorem B is refined mirror symmetry for local P2 is that properties P1 through P4 plus the initial data hold for our definition of the refined free energies. And I guess I don't have time to explain why. So the slogan is that, okay, I guess I'm going to formulate it quite cryptically, is that refinement is really a quantized symplectic transformation acting on the loop space of the cohomology of X. So there is a way to relate, so this is the sort of more professional way to phrase this is that there is an explicit given Tell-Telemann group action with some group element that you can explicitly write down expressing these things through well, the unrefined Gromov-Witten generating series, or even better, the generating series of the descendant theory of the point, so just topological gravity, by the action of some exponentiated quantized quadratic Hamiltonian, which in practice means that there's an explicit graph sum formula that you can write down for these guys. And after a lot of dust settles, you can prove P1, P2, P3, and P4 at that level. I'm over time, so I'll stop here. Thank you. Yeah. Who? Yeah. You could put an AN singularity. Yeah. Yeah, so that would be, you would expect that to give you the, so for example, in the case of the twist, I don't know. Is it gone off? Okay. So for example, if you replace C2 with like a type A resolution, say an Ailey space of type AN minus 1, that would theoretically define for you rank n Gromov-Witten invariance, because that's what it would correspond to rank n DT theory on the threefold. One can try and do calculations along that way. That's certainly something that we're thinking about. And as you say, you can give up. So for example, in the crossover in the Kunkov, there is no requirement on X being a Calabi-Yau. Like you said, you can take some non-trivial fibrations such that Z is a Calabi-Yau 5 with a Calabi-Yau action on it, but X is not a Calabi-Yau. Yeah, I guess that's yeah. In that setting, you would need to match like insertions on both sides of the story. But I haven't done a single calculation in that respect. But that's obviously. Yeah, so the good thing about Gromov-Witten theory is that you can define it on almost anything, unlike DT theory, where like dimension 3 is like super critical, and then you can do something in dimension 4. So yeah, the left-hand side would make sense. How the correspondence goes along, you need to figure it out. But for example, that first example that I was mentioning would be a thing to look at. Uh-huh. Correct. Yeah. Well, X is a torus action on top, though. Okay. Yeah. Yeah. Mhm. Oh no, no, this is something you need to prove. So you know what the worldsheet theory would look like. So you can write down a like a topological single model Lagrangian where you take into account the fact that you have this extra action. So it's just the theory with extra fields for the fourth and fifth dimension, and then you have extra twisted masses coming from the C star action. So you're partly gauging the flavor symmetry on the target, and then I mean this is stuff that goes back to I don't know. It's, Alvarez, Gomez, and Friedman, and then in the topological, the fact that you're taking the topological twist doesn't affect that at all. So you have some massive deformation of uh, original theory. And then, yeah, so I guess what a physicist would like to do would be to show that. So I didn't spend time mentioning the relation to the work of other people, for example, Antoniadis et al. One way would be to see from that perspective, to see their story emerge in some way, or even going back to the roots to see that the sort of effective couplings that are captured by the refinement. So where you're looking at couplings also with the anti-self dual part of the graviphoton appears through through some type of count. But that's okay. I'm not an expert in this because. But the fact that you're breaking conformality on the worksheet seems to it doesn't seem like you can just transport the old arguments into this new story. So this is like evidence at the level of instant on counts if you want. But it would be great to have a like a physics proof that this is the right way to go. And um, hmm. No, there's no beta deformation. This is like a pure genus zero thing. So there's no epsilons in this story. Correct. Yeah. Through the holomorphic anomaly and yeah. Well, the beta, yeah, that's kind. It's a painful story to consider the beta deformation doesn't work for local Cabiaus. Um, there are other beta-like deformations, so it's something that reduces deformation in the 4D limit. And I guess, I mean, the only paper I have in mind is a paper of Kostschatz and Einard, where they wrote down a matrix model and wrote down the thing that you were mentioning, like an epsilon 1, epsilon 2 deformed planar resolvent, such that the ordinary recursion would give you the well, it would reconstruct for you the full open string sector, which I have not discussed at all in this story. But out of that, you can also extract these the same thing that we're computing from the B model. Uh, I don't have much to say because the only so the bestiary consists of a single element, the resolved conifold, and for the resolved conifold, I already have the answer. Um, it would be nice to have something more general than that. But playing with the topological recursion is, for example, if you consider local del Pezzos, is not fun above genus 0. Oh, it says no, it's okay. It's technically more complex, but conceptually the same thing as computing the unrefined invariance in low genus. So the fact that you don't have a Cabio action on the threefold complicates things from the Gromov-Witten perspective, but then something saves the day. The fact that you expect to have some Weyl group action, some symmetry with respect to the full group of automorphism of your fivefold with the five form. It can be used to simplify calculations at some point, but yeah, it's a bit of a bloodbath, but it can be done. For example, we computed explicitly up to genus 2 for local P2. I mean, we computed all these properties to all genera, but if you want to do an explicit calculation, you can do it in terms of modular forms. Mm-hmm. Yeah. If you want to do a lot of, well, if you want to do just localization calculation for some fixed degrees, then it's not particularly different from. At the end of the day, it reduces to some calculation of Hodge integrals on MG, and then you have two extra Hodge classes that keep track of the fact that you have this product with C2. But I mean, there are algorithms to reduce it recursively to the Witten-Kontsevich-Tau function. Yeah, sorry. Are you thinking about Jim and Rahul? Can you be more specific? What do you mean running this? I mean, we definitely use that, for example, in the proof of theorem A1. But what precisely do you have in mind? Oh, the sort of like gluing. Right. Yeah. Yeah, that would be interesting. Yeah. Okay, so with that assumption, the only local curve. Oh, okay. Yeah. No, we haven't checked, for example, because I think you're asking about higher genus curves. Yeah. No, we haven't checked that. Absolutely, it makes sense. Yeah, it makes. Yeah. I mean, remember there was this assumption that I was putting there. Okay. The zero section. Yeah. So already, even if you take P1, the result conival is the only one you've got. If you have like O plus O minus 2, you have this O direction that does have a section. Yeah. It would, yes. Yeah. Yeah, that's what the obstruction bundle looks like when you take this. So it's kind of the definition of what the virtual fundamental cycle for Z is. So yeah. So this would be like it would be the top churn class of say R1 pi push forward F pullback of the structure sheaf on X. So you have you have an H1 contribution, which is that thing, and an H0 contribution that gives you 1 over the weight, which is why you have this 1 over epsilon 1 epsilon 2.